Welcome to our videos about robotics topics. The focus of these videos is on mobile robots, but the math behind the explanations is universal. The next three videos deal with the mechanics of robots. The first video deals with coordinate systems, the representation of vectors and other coordinate systems in them, and the transformation of vectors and coordinate systems between them. The second and third videos are about robot kinematics and dynamics. Coordinate systems are also called frames. The world frame describes a fixed location to which all other coordinate systems refer. For example, the corner of the factory floor. The base frame describes the position of the robot and is usually defined in the base of the robot. The station frame describes the position and orientation of a station where the robot performs an activity, for example an assembly. It is important to use this frame when programming the robot in order to be able to move the station with all the associated path movements. A so-called object frame belongs to an object whose position you have detected with image processing, for example. The wrist frame describes the position of the flange on the wrist of the robot. If no tool or station frame is defined, the position of the wrist frame relative to the base frame usually represents the basic setting of the robot position. The tool frame describes the position of the tool in the case of a gripper, for example, the gripping point in the gripper. This point is called the tool center point TCP. Different tool frames allow the user to switch between different tools without distorting the position description. The goal frame, task frame, or operational frame describes a coordinate system defined by an interaction between robot and environment. It is used, for example, when the force of a polishing tool is to be controlled orthogonally to the surface of a workpiece. World frame, base frame, station frame, and object frame are fixed coordinate systems. They are independent of the position of the robot. Wrist frame and tool frames are moving coordinate systems. They depend on the position of the robot. Target frames are not fixed, but still do not depend on the robot position alone, but on the interaction between robot and environment. Example would be an interaction coordinate system in a contact point, which is needed for contact force control. For mobile robots, the frames are described very similar. The world frame is, for example, the corner of a factory site. Station frames could, for example, describe the locations of battery charging stations or loading and unloading sites. The location of an object we want to grab is described as an object frame. In mobile robots with differential drive, the robot frame is often defined between the two driven wheels. The location of a sensor, for example a LiDAR, is described with a sensor frame. As soon as we mount the gripper to our mobile robot, we describe the location of the tool center point with a tool frame. We could use an operational frame to control a force control docking process at an assembly station. A quick reminder of what a vector and a coordinate system is. A vector, as we use it, is the description of a physical quantity in space with direction and magnitude. A coordinate system consists of three unit vectors arranged orthogonally to each other and denoted by x, y, and z. Calculating the scalar product between vector A and the three unit vectors of the coordinate system, we find the length of the projection of the vector onto the three unit vectors x, y, and z. We refer to these projections as components ax, y, and az. Often one represents a vector in different coordinate systems, while one must designate clearly to which coordinate system one refers, as soon as one speaks of components. As soon as I write the k to the left of the vector in our example, you can see that I mean the component representation of the k coordinate system. If I write nothing, then I speak of the vector and not of the components. So the A vector in the coordinate system K consists of the components AX in K, AY in K, and AZ in K. You can write the identifier for the coordinate system also in front of the parentheses instead of in front of the components. How to describe the orientation of two coordinate systems to each other? In order not to burden this video with the mathematical derivation, I explain the solution here according to the sense. We have given a vector A as a component representation in the coordinate system K, and we want to determine the component of A in the coordinate system J by multiplication with an orientation matrix R. The matrix R with the two indices thus describes the orientation of the coordinate system K with respect to the coordinate system J. The matrix found is extremely descriptive because it consists of the basis vectors of the coordinate system K expressed in the coordinate system J. The index K to the right of the basis vectors indicates to which coordinate systems the basic vectors X, Y, and Z belong. The use of the indices is quite intuitive if you imagine that you can shorten them as you perform the transformation. The orientation matrix R is usually called rotation matrix. This term is actually not accurate in this context, but it is common. The reason for this name is that it can be used not only to represent the coordinate system K with respect to the coordinate system J, but also to perform a rotation of a body from the coordinate system J into the coordinate system K. So we can describe and name the orientation matrix like this. Representation of coordinate system K with respect to the coordinate system J. Representation of K in J. Orientation matrix. Rotation from J to K. Rotation matrix. Since the last two versions are common and short, I will use them as well, even if they are not quite fitting in this context. Of course, several rotation matrices can be combined. The shortening rule helps to keep the overview. To calculate the transformation in the opposite direction, I need the inverse of the rotation matrix. Since the matrix is orthogonal, the inverse is the transposed, which makes our calculation very simple. We often use rotation matrices to describe coordinate systems that are rotated by a fixed angle. One can derive this simply by projecting the vector A in J. For this, one projects A first on the x-axis of J and afterwards on the y-axis of J. AZ remains equal. If we factor out the R matrix, we obtain the rotation matrix by a fixed angle phi. In robotics, these rotation matrices are used very often, which is why we always replace the angle functions with letters for a more compact notation. In the matrix, the one on the diagonal represents the rotation axis in each case, which makes it very easy to generalize the found transformation to other axes. Only for the rotation around Y, we have to use the trick of repeating the matrix to see the solution. The rotation matrix is a transformation we need to transform three vectors like velocities and forces. If we rotate around one axis, we often describe this with rot, the axis specification, and the angle. For a mobile robot, we can use the rotation matrix to transform the velocities and angular velocities. In mobile robotics, it is common to combine velocities and angular velocities in a joint transformation using zero matrices to avoid coupling of the physically completely separate relationships. In planar mobile robotics, we assume that we are moving on a z-plane and therefore Vz, omega x and omega y are zero. This leads to the fact that the corresponding rows and columns of the matrix are obsolete for this special case. Thus, the new matrix is a 3x3 matrix, and the physical relationship can be described very compactly with it. Sometimes in mobile robotics it is called a rotation matrix, but this is incorrect. The vectors consist of a velocity vector and a rotational velocity around the z-axis. The new transformation matrix is a combination of a plane rotation matrix, a 1, a 0 vector, and a transposed 0 vector. The cells of a 3D rotation matrix for rotation around Z are identical with the cells of the found transformation matrix for mobile robots. But attention, it is not one rotation matrix, but two, which were combined for a special case. If one leaves the planar description, one must transform speed and rotation speed with separate three-dimensional rotation matrices. Now we come to describe the position of one coordinate system to another. We know the position of the coordinate system J with respect to I, and we know the position of the coordinate system K with respect to J. From this we want to determine the position of the coordinate system K with respect to the coordinate system I. We get the location vector Rik by adding the vectors Rij and Rjk. For the component notation, we now have to decide on a coordinate system and therefore describe this vector equation in the coordinate system I. However, we do not have the vector Rjk in the I system, but only in the J system, so we pre-multiply it with the rotation matrix Ij. We now see in more detail how a coordinate system is described. On the one hand, we have the location vector in blue, which describes the position, and on the other hand, the rotation matrix with the three different colored unit vectors, which describes the orientation. For the next consideration, we write out the components. We multiply the matrix out and add the R vector. We represent the system of equations as a single matrix multiplication, and we see that we have to add a 1 to the incoming vector so that the location vector is added. In order for the vector to also be transformed further after this transformation, the output vector must also contain a 1 as the last value, which is ensured by introducing a 1 in the matrix in the fourth row and column, and filling the remaining cells of the fourth row with zeros. Now we use vectors again instead of components. The location vector Rik is equal to the homogeneous transformation matrix Tij times the location vector Rjk. If a location vector starts from the origin of the coordinate system in which it is described with its components, the double index can be left out. So in short form, we can now write the transformations of a vector as follows. The homogeneous transformation matrix is the universal description of position and orientation in space and is used in robotics, drones, airplanes, computer games, CAD programs, and so on. At first sign you can see in it the location vector and the unit vectors of the orientation of a coordinate system as they are shown here on the left. However, homogeneous transformation matrices are not always being used. Orientation and position are often stored separately. In particular, the orientation is often not described as a rotation matrix, but as Euler angles or quaternions. Homogeneous transformation matrices can be combined by multiplication, so that I can transform from I to J instead of from J to I need the inverse homogeneous transformation matrix. In contrast to the rotation matrix, the T matrix is not orthogonal and the inverse is not transposed. But we can derive the inverse directly geometrically with some reasoning. The form of the matrix is given. You know where you have to write a 1 and where zeros. The rotation matrix must rotate in the opposite direction. That means it must be inverted, which is in this case the transposed of the rotation matrix. The location vector Rji is simple like Rij, but in the opposite direction. However, Rij is given in the I-coordinate system, and we have to transform it from the I-coordinate system to the J-coordinate system, which we realize with the already inverted rotation matrix. With this, we have found the inverted homogeneous matrix. Now let's turn our attention to mobile robots. If we assume that our mobile robots move around on a flat surface, we can simplify our homogeneous transformation matrix by deleting the third row and column of the rotation matrix and the z component for input and output vector. This leads us to the homogeneous transformation matrix for the plane. Since the robot can only rotate about the z-axis, the rotation matrix reduces to the familiar form cosine phi minus sinus phi, cosine phi. Often orientation and location are stored separately because they are treated completely differently in the algorithms. The position information is stored as a location vector and the orientation as an angle around the z-axis. Let's look how to deal with position vectors using a concrete example. Let's assume we want to know the position of the gripping point of our robot. The position of the robot coordinate system R with respect to the global coordinate system G is described by the vector R, GR and the angle phi. With this we know the rotation matrix and the homogeneous transformation matrix. The position and orientation of the TCP with respect to the robot coordinate system is also known. This allows us to write down the rotation matrix and the homogeneous transformation matrix of the position of T with respect to R. We obtain the overall transformation by multiplying the two homogeneous transformations. With a little reflection, this calculation can be done without the large matrix calculation. Now we also look at our robot example, how we can transform free vectors. Velocities and forces can be transformed from the robot system into the global system by multiplication with the rotational matrix. Since the velocity of our vehicle must always be in the roll direction for kinematic reasons, the speed in y direction is 0 in the R system. Rotational velocities and moments about the z-axis can always be copied for the transformation without calculations. The transformation of velocities and forces between the R and T systems are identical. In this case, we are not only interested in the transformation, but also in the influence of the relative kinematics, which we will discuss in the next video. Therefore, we will not go into it here, but ask you to watch the video about robot kinematics. Thank you for your attention and see you in the next video.